Okay, so assalamu alaikum and good morning. Our new topic is about synchronization, and I think we have seen an example in which we needed to do some kind of coordination between threads cooperating to achieve a task and sharing variables. We have demonstrated that in an application where we had a bank account which is accessible by multiple threads, the same bank account, right? And we have seen that basically the balance, which is one of the attributes in the bank account class, okay, has to be kind of coordinated in terms of the access to it, okay? So today we formally introduce synchronization. We have plenty of topics there, okay, because we have various ways to implement synchronization. However, the concept is the same. Okay, concept is the same, but we can implement it different ways. Towards the end, you're going to use basically one particular way that is the already built-in, okay, synchronization mechanisms that are available in a language, okay, high-level language, or sometimes a little bit of support by the OS. So I'll introduce the problem of synchronization again, but now using a different scenario. We did that in the bank account. Today we're going to do it using the producer-consumer problem, okay? And then we will introduce some of the terms in synchronization, commonly used terms. You have to understand them and be able to explain them. And then we introduce how the cooperatives threads work together to achieve a task, sharing a variable. Basically there, we look at the structure of the code for a cooperative thread, okay? So you should be able always to craft that structure very fast or write it in code, okay? And then we move to the concept of a lock, because we're going to find that it's very important to do the coordination, and one mechanism is using locking mechanism, okay? So accessing to shared data has to be coordinated by a locking mechanism, which means we need to obtain the lock before accessing shared data, release it after the shared data is accessed to give chance to others, and so. So that concept of a lock can be implemented in various ways, okay? So here we branch. After this, we branch to the different implementations of the lock. The very first implementation is by using algorithmic way, which means we're going to craft an algorithm in which it will represent a lock, okay? Thinking that it's going to represent a lock. So we're going to have a few attempts to implement a valid lock, okay? Using an algorithm of our own. In fact, we're going to use that in the literature, and there are 3 different implementations or attempts to implement the lock. The third one of them is successful. The first 2 are not, but we still present them, okay, so that you have the kind of critical thinking of implementing the lock, right, rather than just present the successful attempt immediately, okay? So that is one way of implementing the lock, and then we have other ways of implementing the locking mechanism, including using some atomic instructions that are supported by hardware. So we can use that to implement the logic of the lock, and we're going to show you how to do that as well. And then we look at other implementation of the lock, which can be with the support of high-level languages. To do that, we will show an example of Java, how we can use the Java language to implement the lock, okay, using some of the methods that are available there in Java. And in fact, you have seen one keyword that's very important. It's called what? Anybody? Synchronized. Do you remember the method when we use synchronized? We said it is used to activate the default lock of an object, right? Okay, we're going to talk about that in details. Then we will demonstrate some of the classical problems of synchronization, okay? Problems where synchronization arises there, the need for it arises. These are producer-consumer problem, readers-writers problem, and dining philosophers problem. So we will show you the solution using Java synchronization, right? After that, we will move again to another branch of implementing the locking mechanism. And here is going to be using semaphores, the concept of a semaphore. So we'll introduce that concept to you, and then we'll show you how can you use semaphore to implement, okay, synchronization for various problems, including the most common problem, which we call the critical section problem, producer-consumer problem, readers-writers problem, and the dining philosophers as well. Solutions with semaphore, right? And finally, we will end up with looking at the API support for synchronization, in particular Java API support for synchronization. So you'll find that actually there is a package in Java which is called concurrent package, okay, and it has very useful classes that you can use to do what? To implement synchronization for various problems, okay? So that would be the easiest for you, actually, the last option. But however, you've seen all different options of implementing what? Synchronization. Now, in parallel with this, okay, if you want to know how synchronization can be implemented with C, okay, as another example of high-level languages, then I think I'm encouraging every one of you to look at material that explains how C supports synchronization, or how can you solve these classical problems using what? C synchronization, okay? Similar concepts. You will find that there is a semaphore in C as that in Java as well, okay? And other things as well, okay? Right. So the idea of synchronization, okay, is a need when we have processes who are cooperating together and sharing data, right? And most, softwares nowadays, okay, they make use of the already available parallelism in the hardware itself. Having multi-core and hyper-threading for each core, I think software, now they are moving, okay, for the last decades or one or two decades, they are moving towards something like this, utilizing it at the programming level, rather than just leaving the concurrency to be structured by the OS and the underlying hardware, because OS also, they support the auto concurrency, okay, for certain instructions, pipelining, okay, and making use of the CPUs, right? The available CPUs, as we've seen with the Linux scheduler, for example, right? Utilizing the multiple CPUs, okay, and having multiple queues in there. But also at the instructions, okay, at the code of one particular process, okay, we have some kind of parallel instructions that can work together. So we have sequential programming. This is dated already, right? Outdated. Now what we're moving to is concurrency programming, where tasks that can be run in parallel, we need to make sure that it does, okay, and that is at the software level. Now this kind of concurrency can be either logical concurrency, in which you use the threads and you are not sure whether these threads will run on physically independent CPUs or CPU environments, or they will run on one CPU and they have some kind of time sharing, correct? But naturally, okay, that kind of implementation, if you have a single processor, then that's multi-threaded programming, and threads, they will take turns. And if you have multiple processors together, okay, for example, in a parallel machine, or even within one computer system that has multiple processors, then they will run on parallel. The way that you design it as a programmer, they will run. Or sometimes we have a distributed environment in which we have nodes that are separated far from each other. They're connected by a network, and then we can implement, okay, that kind of synchronization. But here, the concepts are a little bit different, okay? Still uses some of the concepts of multi-threading, but we still have to consider other factors when we code for distributed systems, okay? Now, to introduce the problem of synchronization, we go for the classical example, which is producer-consumer problem. The idea is that we have two active threads, they are cooperating, or two types of active threads. They are cooperating in a sense that one type will be producing items, the other type will be what? Consuming items, the producer and the consumer. Now, the consumption and the production of items will be using a buffer that both of them share, okay? So the producer produces an item and inserts it in the buffer, and the consumer consumes an item from the buffer. Plus the other constraints that everyone should be aware of, that is, if the buffer full, then the producer is blocked, cannot insert, right? And if the buffer is empty, the consumer is blocked, cannot remove, right? Cannot consume, right? Now this buffer also comes with different type of implementations. It can be infinite buffer, where the size basically is infinite, which means, but there is no such thing, right? An infinite buffer. However, here the assumption is that the buffer is of very large size, that regardless of the speed of the producer, it will not be filled up, okay? The other implementation, the buffer has a particular size which is greater than 1, okay, greater than 1. So we can have multiple items in there, but it has a maximum size. And then one implementation where the buffer has one single location, We can merge the last two in one, okay, which is bounded buffer, we call it. And the very first one, we call it unbounded buffer. However, regardless whether this buffer is bounded or unbounded, it has two main operations. Basically, the insert and remove operation, right? So regardless of the implementation, we have these two operations. Insert, that receives the item, and if you want to go generic for the item, then we can say the type of it is object, right? And remove, that removes an item, and again, it removes what? An object. Then based on the application, you can cast it back, okay? The one who's gonna call the remove method is who? The consumer. And the one calling the insert method is the producer, right? But both of them work on the same shared object buffer, right? So now if we want to model this, we can say that the buffer can have it as an interface, okay? Interface buffer. And we can have two classes to implement this interface, bounded buffer and unbounded buffer. Now, if you notice that the interface has two methods, which are the ones that we mentioned, okay? These methods are insert and remove. Of course, as you know, we put there the public abstract, but you cannot to have it in there because that's the default of whatever method you have in the interface, just to remind you, right? Okay. So now we look at the bounded buffer itself and its implementation. So bounded buffer implements interface buffer, right? So I'm expecting that I have a fixed number of locations. Let's say that we have 5 locations in this buffer. We have some items already there in the locations. There is an insert end and there is a remove end. So this is the remove end, out. And this is the insert end in. So in always points to an empty location, right? An empty location, and out points at a location that has an item to consume. So we can define, so in this case, I always keep track of what? Count, which is the number of elements that I have in the buffer. Now, the rest of the implementation, the size, here I fixed it to be a constant final there of 5. And if, and the count to keeps the number of elements, as well as I have in and out, okay? These two to point at the locations needed for insertion and removing an item. The buffer itself is implemented as an array, okay? Array of objects, because we can't save any type of item, right? Clear until this point? So now we are left with what? With the implementation of 2 methods, okay? So this class must implement 2 methods from the interface buffer. The methods are insert and remove, okay? But also we need to do some kind of initialization in the constructor, for example, for out and for in, right? So for that, we need to set a value for out, a value for in, and a value for count. Initially, all of these are what? Zeros, okay? And we dynamically here, well, in this case, allocate the memory that is needed for the array. So that's the kind of initialization. You need to have it in the constructor, okay? Next, we'll move to the methods. We start by the insert method. Insert method is called by the producer, right? It receives an object, and then it's supposed to do the insertion. However, there is a constraint. The constraint is, so if buffer is full, this method won't return, blocked. What does it mean when is blocked? What does it mean blocked? Means does not return, because the one who's gonna call this method is whom? Producer. Okay, producer is gonna call the method of this class, bounded buffer, right? And if it returns, means the producer already inserted, right? Then the producer continues. But if it doesn't return, means blocked. So we can implement that by using a while loop, saying that while count equals buffer size, it means it's full. And in this case, the method keeps what? Checking the condition. Keep checking the condition, hoping that the condition will change, will become false. However, who's the only one who can make this condition false? A consumer calling remove, right? Because the consumer calling remove will reduce count, right? Will reduce count. But during the time slice given to the producer, calling insert, will anything change? During the time slice, the producer is active. Will anything change if count equals buffer? Will it change during that time slice? Who's active during that time slice? Only producer. Consumer is not active. So will it change? No. However, the producer is still running, calling insert, and continuously checking a condition, okay? Waiting for it to change. So making the whole system busy, okay, checking a condition that won't change during the time slice given to the producer, okay? Correct? So that's why we call this kind of loop busy wait, or this kind of implementation what? Busy wait, because you're waiting, you're making the system busy, but nothing is changing, okay? Oh, why don't we implement the blocking? Now, if count is not equal to buffer, means we have some empty locations, and in that case, the producer would proceed to insert the object, right? So the insertion is done by incrementing count, and then inserting the item in the location pointed at by n, so say buffer n equals item, and then after that, we increment n. The next position, okay, is the one after that, right? But because we have it here bounded array, we might reach the end, so we need to iterate back to the front. So we take the modulus with the size. Clear? Yep? Okay. Now we have a similar implementation for the remove. The busy wait here is with the condition while count equals 0, while no items in the buffer, then keep checking this. The method will not return, right? So if no items, consumer is blocked calling this method. But if there are items, then we proceed after the while loop. So this is the empty while loop, right? Proceed after the while loop. Consuming the item means the count will be less 1. And then we're going to save this item so that we can return it in the last statement. Then we increment out to go for the next item to be what? Removed. out equals out plus 1 modulus, again, buffer size. Clear? Yeah? Any question? Excellent. Now let's look again at this code. In particular, let's look at the busy wait. Busy wait, we said, within the time slice given to the producer calling insert, if the buffer is full, okay, then the producer will be consuming that time slice, hoping the condition will change, but it will not. Correct? Yes? Because that's the only active thread at that time. Can you give me a scenario in which this condition will really change within the time slice of the producer? Come on, it's easy. Okay, let's go back to the reason why it did not change. It did not change because during that time slice, who's running? Only the producer. So for it to change, a consumer must run. At the same time, the producer is running in its time slice. Would that be possible if we have one processor? But if we have more, it's possible, right? So in that case, this busy wait implementation is good, right? Well, I said it's good. It works, right? Because during the time checking, maybe the consumer running on some other execution environment, okay, processor, and then might change that condition, correct? Now, how good is that? It works, but how good it is? Okay, let's look at an implementation in which we don't have busy wait. Okay, an implementation in which you don't have busy wait can be like this. While count, this is for the insert method, okay, that is called by the producer. Okay, I can have while count equals buffer size. Then I will not have an empty body for the while loop. I will have something in the while loop, one statement. Okay? So I'm saying that if the buffer is full, give chance to the other thread to run. So what should this thread do? And who's this thread? The producer, because he's the only one who can call insert, right? Give chance to others. How would a thread give chance to others? By suspending itself, right? Suspending itself. And when it resumes back, it will resume back to the body of the while loop. That's why we have a while loop, not if statement. Correct? To go back to the while loop, keep checking again, right? When it resumes back. But if you have if statement, that's it. You are out of the if statement. That's totally wrong. Okay? Do you understand why we have while, not if? Okay? Okay. So suspend yourself if the buffer is full. How can I do that? What's the suspend method? For example, here in Java, we have it even in threads, C threads, POSIX, P thread underscore yield, right? Do you remember that? Yield. The same method is in Java, okay? So I can have what? While count equals buffer size, yield, okay? Got it? So by that, the thread suspends itself, giving chance to the other thread to run. And it will work for what? On a single CPU. So you don't have to consume the whole time slice. The producer does not have to consume the whole time slice if the buffer is full. Yield, suspend yourself. So increasing possibilities that the consumer will run, okay, and then you can resume back. However, yield involves suspension. So we have what? Thread context switching. And thread context switching is what? Time consuming, overhead. Excellent, right? So if the time needed for the context switching is more than the time in which the consumer will run on another processor, then the implementation of busy wait is much better, right? rather than you do context switching, because context switching is expensive. So if you want to really to see how good it is busy wait with multiple processors, then we have to look at the time of context switching, okay, and the time, okay, or the frequency of the consumer running, okay, compared to that of the producer as well. Got it? Okay. I mean, we're trying to like discuss a few ideas, okay, at the code of synchronization. Synchronization, you need to have some critical thinking in there, a simple one. Now, to most of the code that you'll see later on, okay, it will be using an active thread, okay, the code of the active thread running, and this thread will be executing a code that has nothing to do with shared variables. And it will execute some code that has something to do with accessing shared variables. Correct? Yeah? Yes? I mean, not all the time, the thread, okay, in general, okay, not all the time, the thread will be doing what? Accessing to shared variable, right? Sometimes it might need to access shared variable. Sometimes it might not, okay? The critical point is the point of accessing what? The shared variable. Here we need synchronization, correct? But for accessing non-shared variables, it's fine. The two, they can run simultaneously and don't be any problem with the execution of cooperative threads. But when there is the portion of the code that has something to do with accessing shared variable, that's a critical code. Critical code. So we say that actually a thread will be doing some kind of critical work and non-critical work. The critical work, okay, has to be what? Guarded. Okay, has to be coordinated. That's the general implementation of a cooperative threads, which we're going to show you in a while. Now let's look at the implementation of a producer. Producer producing. So basically it works on an object which is buffer. The same thing for the consumer in a while you're going to see. It works on the same object. So in the main application, we're going to create an object of buffer, and we're going to send it to what? Two objects, one of them of type producer, the other of type consumer. The same object of buffer will be sent to both of them so that they can share it. Okay? Now, what the producer will be doing, okay, continuously will be producing items. Now, I implemented the production, okay, of items, producing items. I implemented by a time that is needed to produce. Okay? So this is how we model it. That time, I can say it's the time of random time. Some items might be produced in 10 units of time, others of 100 units of time, and so on. So basically, we have the thread to sleep, okay, in that time. Here we are modeling what? The production time, okay? So we have sleeping time. I have sleep for random time, and then I'm printing just a message there saying that the producer is napping, right, for that time, and I'm doing the actual sleep. The actual sleep should be done by using what? Sleep, okay? Sleep. So we have to do that by calling sleep, and the way we call it, okay, thread dot, okay, sleep. So thread dot sleep, okay, implements the sleeping for that random amount of time. Now then the actual production, let's say that the item is a date object. It could be anything, right? So that date object now has to be inserted in the shared buffer. The insertion is done by calling the specific method of the bounded buffer object. So I'm saying buffer.insert. Buffer.insert. That's what the producer is doing. Okay? The consumer, on the other hand, does something similar. It receives an object of type buffer, and it does the sleeping, which is the time needing to consume. Okay? And then it does what? The actual receiving of the object. So that is by calling remove. The method remove from the object buffer. So buffer.remove, and what we're removing is a date object, so we can cast it back to a date object, do whatever we want to do with it. Clear? Okay. Now, what's good about the code here, the consumer and the producer, this code can work for bounded buffer and unbounded buffer. The same code. Can anyone tell me why? Why this code can work for a bounded buffer or even unbounded buffer? Look at the constructor. It receives an object of type interface buffer. Okay? A bounded buffer object or unbounded buffer object, both are of type buffer. Okay? So this is a good thing about this implementation. Right. Now, in the main class, what you need to do is basically to create an object of buffer. Okay? And that's what we're doing in here, buffer. Okay? And then create what? A producer and a consumer. Producer and a consumer. Sending the same object buffer to both of them so that they can share it. And then start them. Then what? Start them. If you notice here that the way we start them reflects that these two are threads and they have been implemented by implementing the interface runnable, right? So if you start one producer and one consumer, we are demonstrating actually how they share. But also at the same time, you can start multiple producers, multiple consumers as well, okay? Now, what we needed here, okay? So you know now the scenario producer-consumer problem and the implementation, full implementation of it, correct? Now, who's using, or, let me just, sorry. Looking at this code, okay? Code of producer, of insert and remove. They share the object buffer, right? And we think that they should work nicely, okay? However, what is the actual shared value in the object buffer that might cause a problem? The object buffer has defined count, defined in, defined out, and defined maximum size, correct? This is the data inside it. Maximum size is a constant and it's not changed by any of these two methods, correct? Okay, in and out and count as well, they are changed. The two methods, they change. Now let's see in. Who's changing it? Which method? Which method changes in? Insert, okay, the insert, which is called by the producer, okay? But does the consumer change in when calling the remove? No, so that shouldn't be a problem. So n is not the problem, right? Is not the one that's shared among them or between them. Now let's look at out. It's changed by the consumer, but it's not changed by the producer. So that's not the problem at all, right? Look at count. Count is accessed by both of them. So if they're running simultaneously, okay, that might cause a problem. Knowing that count here is accessible in one statement, okay, but this is a high-level statement, plus plus count minus minus count. However, we said this involves 3 instructions, and an interrupt can happen in between instructions, correct? Leaving the count in an inconsistent state, okay? To demonstrate that, let me give you this scenario. Having count plus plus executing these instructions, moving a value of count to a register, and then incrementing the register by 1, and then storing back the value of the register in count. These are the generic, say, regardless of following an instruction set, these are generic, okay, this is a generic way of incrementing count by adding 1. And the decrement is done similarly. 3 instructions, okay? Now, let's follow this scenario. We have count equals 5. Count equals 5. One would state, we look at the system, we found count equals to 5. There are 5 items. And now, At this point of time, we have the producer executing what? The insert. In particular, the producer now is executing the statement which is count plus plus. Okay? So the very first instruction is to move the value of count to register 1, which is 5 in register 1. But count is still 5. And then, after that, increment that, register by 1, so we have 6 in register 1, but count is still 5. At this point of time, we have context switch. Context switch. Now, who's running? Consumer calling remove. In particular, now executing count or minus minus counts. Okay? And that will result in moving the value of count in register 2. So register 2 has 5. Decrementing register 2. Now register 2 has 4. Okay? At this point of time, I have a context switch. So count is still 5. Right? In the code of the insert and remove, count is still 5. However, register 1 is 6 and register 2 is 4. Now producer proceeds, okay, resumes, and will save the value of register 1 in count, resulting in count being 6. And then context switch, we have the consumer now resumes, saving the value of register 2 in count, so count is 4. So the final value is like this. For the producer, count is 6, and for the consumer, count is 4. While actually, even the value of count is none of them. Because we had 5, we have 1 item produced, 1 item consumed, so we again have 5. So this is totally, this is the worst case, in which the 3 values are different. The one that should be, the one that is seen by the producer, and the one that is seen by the consumer. So this is inconsistent view of the data. Do you understand? Okay. So incrementing or decrementing count, accessing this particular shared attribute of the object buffer should be guarded. We have to coordinate, okay, the access to count. So now the problem becomes more specific. Correct? Now we define few terms related to synchronization. Okay. So basically, synchronization is needed when we have cooperative threads accessing shared variable where at least one of the access is an update, right? If none is updating, even though the access come, but nobody is updating, it's fine. They can run simultaneously, no problem. We define what's called the race condition. The race condition is a situation where the final value, okay, of the shared variable depends on the order of the execution for these cooperative threads. And just now we had one order. We use context switching to have a particular order. Right? So this is called the race condition. So all you're seeing is a race condition. And then the critical section is that portion of the code in which a shared variable is accessed. Okay? Knowing that the access of at least one of the cooperative threads is an update. Right? The rest means the rest of the code is non-critical section. Right? The rest of the code is non-critical section. The only thing that we need to worry about is the critical section. Okay? And then synchronization is the mechanism, okay, that we use to control the relative order, okay, of access to this shared variable to ensure that it has a consistent view. Clear? Okay, these are some of the terminologies. So in general, I can say a cooperative thread basically will be doing particular acts, mainly 2 things. Accessing critical section, a portion of the code that will be accessing critical section, and another portion that has nothing to do with the critical section. So we call them critical section and non-critical section of the code. Okay? The idea of synchronization is to guard the execution of critical section. So we need to do something before entering critical section, as well as something after finishing critical section. Okay? So from here comes the idea of the lock. So we can say that the critical section, okay, to access it as a cooperative thread, you need to obtain the lock. And only one thread can have the lock at any given time. So if one has it, no other thread can have it. And once you finish critical section, if you have the lock as a cooperative thread, what you need to do is to give chance to other cooperative threads to execute their own critical section if they need to. So that can be done by releasing the lock. Releasing the lock. So you can think of the code before entering critical section is what? Obtaining the lock, acquiring the lock. Or we can just simply call it a code that is needed to obtain the lock or acquire the lock. We can call it the code of entering the critical section, the pre-code, right? And the exit code can be release lock, unlock, or the code to give chance to other cooperative threads to enter their critical section. So we can just call it what? Leaving critical section code. Something that a cooperative thread must do. Okay? So that's the concept of the lock, as I mentioned before. It's one way of doing synchronization. We have acquire and release pairs of methods. They have different names. You've seen that in green. Acquire, hold, lock, or release, give away, and lock. These are the common names used in the literature. So what we need to do is to provide an implementation of, now algorithmic implementation of this lock. Okay? But for an algorithmic implementation of the lock to be valid implementation, to say that this lock works, then 3 conditions must be satisfied. The very first condition, we call it mutual exclusion. Mutual exclusion says that there is only one, okay, at most, one active thread in its critical section at any given time. You can't have more than one thread. That's the very first condition. The second condition, progress. Progress, I put it in my statement. If there is a cooperative thread willing to enter its critical section, and at that time, no other thread in its critical section, then it should be granted. It should be granted. If no other thread in critical section, and one of the threads is willing to enter, then there shouldn't be any reason for it not to enter. Right? That is what? Progress. Bounded weight implements fairness. Implements fairness. There should be a bounded number of times for a thread requesting to enter a critical section to be granted, with respect to the number of times a thread continuously entering its critical section. So we don't want to see a thread continuously entering critical section while others requested that, okay, other threads requested that much earlier, but they were not given the chance to, okay? 3 conditions. If you have an implementation that satisfies them, we say you have the lock. You have a valid lock of the, a valid implementation of the lock. Now, we're going to do that by a logic, an algorithm. This algorithm implements the lock. The lock must have 2 methods, lock and lock, right? Acquire, release. Here we call them entering critical section and leaving critical section. Okay? So these are the two methods you're going to see in the class. That is the first attempt to enter what? The lock. But before going to the algorithms, let's show you the code, the generic code of a cooperative thread who is executing critical section and non-critical section. Okay? So if you're going to code a thread in a critical section problem, then you need to say, it's a class that implements a thread. Commonly in literature, we call this class worker, because we have multiple workers, right? Worker implements runnable or extends thread. That's the class. And then after that, you have this worker receiving a lock. Receiving a lock, because there is only one lock in your system. If you have multiple locks, what's the use? Exactly. The door, okay, I mean, consider that the room is, okay, where we have the shared data. If it has one door, okay, and it has a lock, yes, we guarantee that there is only one in. But if it has two doors, two locks, we can guarantee that. So the idea, it receives a lock, as you see in here, and the lock, we can have different ways of implementing it. Basically, we call it what? Mutual exclusion. Mutual exclusion, because we're going to have different implementations of the lock. However, this is an interface, mutual exclusion, okay, that has two methods: entering critical section, leaving critical section, similar to what we just seen for the buffer, right? It receives an ID and a name, okay? And what does it do, this thread? It does enter critical section, which is here, okay? Executes critical section, right? And executing critical section is what? Actually being busy for a while, correct? So this is a method, a utility method that does the sleeping for a while. So to have a clean code here, we have a class, call it what? Mutual exclusion utilities, okay? And it has a method, which is critical section, another one, non-critical section. And what's the code of these methods? Sleep for a while. Random number, sleep. Correct? So we can, even if you don't want to have this class here, you can just have random sleep. And here what? Random sleep. Random sleep to model the critical section, and random sleep here to model non-critical section. Busy doing something. That's where you do the code, right? Now, this is the new thing here. We are calling the method entering critical section of the lock and leaving critical section of the lock. So we're guarding what? We are guarding the critical section. Correct? Something that you have to do before you enter a critical section, and something that the thread must do, okay? Leaving the critical section. So we're going to have three different attempts, okay? Three different implementation of the lock. And this implementation is going to be algorithm 1, algorithm 2, and algorithm 3. So these are lock 1, lock 2, lock 3, right? Locks. But each one of them must provide implementation of these methods, entering and leaving critical section. And in the main class, what do you do? Basically, you need to create an object of the lock, correct? And then pass it to whom? To two workers who are sharing this lock, but they are executing critical section. Right? So we have here creating a one algorithm. It could be algorithm 1, 2, or 3. Here I'm creating what? Algorithm 3. Means I'm using an implementation of algorithm 3 for the lock. Right? I'm sending that to the first worker and to the second worker and starting them. Clear? So that's the general framework of the application that will be using these three algorithms. Do you have any question? Okay, next time then we're going to demonstrate to you algorithm 1, 2, 3 and proceed from there